This video shows a simple block diagram of a Doppler radar. It describes the tasks of the individual components up to the plot extractor. It also includes a brief overview of historical and current surveillance radar displays. Radar works similarly to an acoustic echo. From the delay time between the call and the echo, the distance of the reflecting obstacle can be calculated. With acoustic echo, both a loud voice and good ears are required. With radar, a powerful high-frequency transmitter takes over the function of the loud voice. A sensitive receiver replaces the good ears. The radar transmitter often has a pulse power in the kilowatt range, in the past even megawatts. The receiver must be able to process signals in the picowatt range. The ratio of received power and transmitted power can be about 1 to a quadrillion. For comparison, the chance of winning the jackpot in the lottery is about 7 million times larger. In the past, the first radar tests involved separate antennas for the transmitter and receiver, such as the British chain home during World War II. In the case of modern radar sets, dislocating the transmitting and receiving antennas in different sites is still possible. This design is known as bistatic radar. This technique is often used in strategic over-the-horizon radars. In most cases, however, a shared antenna is used. This is then called monostatic radar. However, different antennas can also be used directly next to or above each other. This design is named quasi-monostatic radar. The criterion for the designation, monostatic, is that the calculation of the target distance can be made in the same way as is typical for monostatic radars. That is, the outward and return paths are of equal length and the one-way distance to the reflector can be calculated from the delay time by halving it. If only one antenna is used, then a duplexer, or transmit-receive switch, is required. It switches the antenna to the transmitter at the moment of transmission and protects the receiver from overload due to the high transmission power. During reception, it routes the echo signals to the receiver with as little loss as possible. The switching times must be as short as possible. These are in the range of a few nanoseconds. At lower powers, a ferrite circulator can be used for this purpose. This has the advantage that transmission and reception can take place simultaneously. At higher powers, the receiver must be switched off during transmission time. This switching creates an area in which the radar is blind, because as long as it is transmitting, the antenna is busy and cannot receive. With a transmission pulse of 10 microseconds length, this blind area already has a diameter of 3 kilometers. A pulse radar operates according to a strict schedule. The transmitter's trigger pulse determines the starting point of the energy transmission and often also the duration of the transmission pulse. The pulse repetition frequency controls the interval between two transmit pulses. For short ranges, the pulse repetition frequency can be very high in the kilohertz range, while long-range radars have a lower pulse repetition frequency. Although electromagnetic waves propagate at the speed of light, long ranges result in significant runtimes. 1 microsecond represents a range of 150 meters, which means that at 1,500 kilometers, this runtime is 10 milliseconds and requires a pulse repetition frequency of less than 100 Hz. In general, almost all radar components require clock pulses, which are also provided by the synchronizer block. It also generates timing marks, switching gates, and trigger pulses for the display units. In the past, radar displays had a problem. They could only display one diagram from a maximum of 2 measured radar values on a usually limited screen area. In the past, there were some radar displays specialized for different applications. Modern devices always use a computer screen. Representative of a large number of radar scopes, a simple oscilloscope is shown here as an analog A-scope. This screen is also only a computer-generated image. The A-scope shows a video amplitude as a function of time. The linear x deflection is proportional to the propagation speed of the electromagnetic waves in space. Thus, the runtime is proportional to the distance from the reflector. The transmitting pulse also bounces through the receiver circuits. Time delays in the internal circuits are compensated on the oscilloscope. The runtime is measured from the leading edge of the shown transmit pulse to the leading edge of the echo signal. Both pulses pass through the same circuits and thus always have the same internal delay time. Ancient display units always used a cathode ray tube for display. Displays for radar were divided into units with deflection modulation and units with brightness modulation. At deflection modulation, a temporal deflection in one direction was superimposed by a deflection at right angles to the timeline. The simplest version was the A-scope, which functioned like a cathode ray oscillograph. With the same screen diameter, the J-scope had better resolution due to the circular deflection of the time beam but took some getting used to. The radar with an L-scope was used in historical fighter planes. It used two antennas squinting to the left and right. Their echo signals were alternately displayed alternately to the left or to the right of the center of the screen. If both antennas received an echo signal of equal strength, then the target was on course. A synthetic radar image no longer consists directly of the analog echo signals but of the graphical display of the digitized data with information about this echo signal. The size or strength of this echo signal isn't shown here but the information only, that there is a target with a given course and speed, and its coordinates are completed with additional information from secondary radar. This picture is only a section of a screenshot of more than twice the size of an air traffic control radar. Its monitor must have the highest possible technical resolution in order to display all information about the air situation. To generate such an image, considerable computing power is required. Today's computer technology can easily manage this. In the radar signal processor, the echo signals are still processed as a signal either analog or digital. Delays of 1 to 2 or 3 pulse periods are expected here, especially if a Doppler frequency is to be measured. However, the delay times are relatively constant so one can still speak of processing in real time. With the radar data processors, these delay times are no longer constant. Here delays of several complete antenna rotations can accumulate. For this reason, a timestamp must be supplied with the dataset during digitization to be able to evaluate the timeliness of the data. The echo signal is digitized as early as possible, usually already at the intermediate frequency level, but sometimes also directly as a high-frequency signal. Parts of the receiver, the radar signal processor, and the radar data processor are then only software solutions. The entire control of the radar can also be performed from the computer, starting from switching on and off, through the selection of operating modes, to the targeted modification of radar parameters. For example, the transmitting power can be reduced. Possibly the transmitting pulse can be given an adapted internal coding, and, in case of hardware failures, a module held in readiness for this purpose can be changed fully automatically. The operating system of this computer is usually a specially compiled Unix version. Often an own GPS receiver belongs to the radar, to generate an exact time indication. An important function in a radar set is the suppression of fixed targets or the moving target indication, MTI. Not only aircraft but also every tree, every mountain, and every house also generates an echo signal. At a larger distance, such fixed targets disappear behind the horizon, but at close range, they form a disturbing backdrop, so-called clutter. The echo signals received by radar thus consist of a composite of many undesired signals, among which the desired echo signals are hardly discernible. Modern radar sets have many filter options to suppress these interfering signals and display only the desired echo signals. The phase angle of the echo signal is the phase difference, phi, between the transmitted signal and the echo signal. It results from the delay by the runtime, which is the ratio of the distance to the target, and back, as a multiple of the wavelength. Unfortunately, phase cannot be used as a measure of a target distance since ambiguity appears because of the periodicity of the sinusoidal oscillation. One cannot determine how many full wavelengths fit into this distance to the target and back. If necessary, one can only measure whether the phase difference between the transmitted signal and the echo signal is constant or whether it changes continuously, and if so, how fast. A continuously changing phase is also a frequency, here a Doppler frequency. The phase shift of the echo signal is evaluated to distinguish a moving target from a stationary fixed target. The Doppler frequency can be experienced best on a fast-passing car. If the distance between the sound source and the observer is constant, then the observer hears the engine noise at a constant pitch. If the car drives toward the observer, there is a compression of the signal, which the observer perceives as a higher frequency. If the car drives past the observer, there is a stretching of the signal, which is perceived as a lower frequency. It should also be noted that the faster the car travels, the more pronounced the effect. This effect occurs with all signals that propagate at a constant speed. This effect was first described by the Austrian physicist Christian Doppler, and the difference between the sound sent and the sound heard is called the Doppler frequency. Electromagnetic waves that strike a moving target behave in the same way. Electromagnetic waves propagate at approximately the speed of light. This propagation speed is constant in the respective medium and thus the Doppler effect also occurs here. From the Doppler frequency, the velocity versus can be calculated directly. It is only an approximation equation based on the fact that even a very fast airplane flies much slower than the speed of light. Factor 2 expresses that the Doppler frequency occurs twice with radar, the first time during the way from the radar to the target, and the second time for the now already with the Doppler frequency of the outward way affected reflected signal on the way back to the radar. Coherence in radar refers exclusively to a defined phase relationship between the transmitted signal and the received signal. In a fully coherent radar, all transmitted signals are derived from a constant oscillation of a master oscillator. This makes it possible to measure phase changes of the echo signal between pulse periods and thus distinguish moving targets from fixed targets based on a Doppler frequency. This assumes that the transmitter is a power amplifier type. Solid-state transmitters are almost always fully coherent. Also, some vacuum tubes can produce coherent signals when used as amplifiers. Mostly traveling wave tubes or klystrons are used for this purpose. Only a short section of the constant oscillation of the low-power oscillator is ever cut out, amplified, and transmitted. Non-coherent radars use a high-power oscillator. In the very high frequency range, this can still be a triode or tetrode. At higher frequencies, it is usually a magnetron. The phase position at the start of the oscillation in a high-power oscillator is undetermined and chaotic. This means that no Doppler frequency can be measured, and thus, moving targets cannot be distinguished from fixed targets. However, there is a circuit trick in which the transmit signal synchronizes a coherent oscillator, which then continues to oscillate with the phase of the transmitter during the reception time, thus storing the phase of the transmit signal. These radar sets are then called pseudo-coherent or coherent on the receive path. In this way, a radar with a magnetron transmitter can also detect moving targets, although not as effectively as a fully coherent radar. A Doppler frequency can be measured quite accurately by the rate of change of the phase position of the echo signal. To do this, the echo signals from two or more pulse periods must be compared. The complete procedure is given the name moving target indication, MTI. The pulse pair processing is only a part of it. The whole process is part of the radar signal processing. However, this pulse pair processing can also be performed digitally on the computer. In the phase detector, the phase of the echo signal is compared with a reference frequency. This reference is either provided by a coherent oscillator or derived directly from the master oscillator for the transmitter's carrier frequency. Fixed targets have the same phase shift in each pulse period. Following that, they have the same amplitude after the phase detector. Moving targets have a variable phase shift pulse to pulse. After the phase detector, they have a bipolar video signal. The amplitude of moving targets varies very quickly between the positive and negative maximum. A complete pulse period is buffered in a suitable memory and compared with the following pulse period. In the subtraction stage, fixed targets cancel each other out. The subtraction of both pulse periods from a bipolar video results in a non-zero amplitude. The faster the phase shift changes, the stronger their difference. Slow differences appear with very slow-moving targets or targets flying tangentially to the radar. 3 or 4 pulse periods may be compared for better detection of slow-moving targets. Since this process is usually already digital, the intermediate storage of several pulse periods is no problem. To generate such a synthetic radar image, not only the fixed targets have to be suppressed. With a plot extractor, symbolic target signs are generated from the analog or already digitized radar data, which still describe an echo signal. Up to then, it was called radar signal processing. In nearly real time, afterwards, it is called radar data processing. For this purpose, the data from several radar sets are linked together. Additional information is provided by a secondary radar, which is still called radar, but is rather a bidirectional data exchange with the respective aircraft. A timestamp is generated from a GPS receiver. Each current location of a target is a plot. This term comes from the earlier plotter, the person who drew these target signs on a planchette. New plots are linked to the older plots to form a track. Older plots of this track are displayed as a dotted line behind the current plot as a slowly fading history. A small bright line at the symbol shows the current course of the aircraft, which does not always have to match the history. The additional information, altitude, identifier, airline, time, is displayed in an alphanumeric block next to the target symbol. For example, the target sign on the left side of the screen KLM 1199, an aircraft of Royal Dutch Airlines, identifier 3160, altitude 28,000 feet. This screenshot is from the German air defense radar in Aurich, Brock Z-Tel. This can get confusing at very large scales. But the image can be displayed on any number of computer screens and every radar user can enlarge the display on his screen, so that the targets which are particularly important here can be displayed enlarged without an identification signal, in yellow. The font size remains constant. The blocks of additional information can also be displayed only for specific target signs by choice. For example, the 2 military aircraft marked as important in yellow, which are practicing an intercept over the North Sea, and the clicked aircraft of Royal Dutch Airlines, KLM. I hope you enjoyed the video and thank you for your attention.